Welcome back, everyone. Hope you had a nice weekend. If you didn't get a chance to sort of go over and review 4.1 and 4.2 basic, or 4.3, that's what today's activity really is. It's applied problems that take us back to 4.1 and 4.2. So today's 4.5 is actually more of a review. But it's like when we did related rates, the hard part is going to be getting it set up. Once you've got it set up, following the process to find maximums and minimums is not so bad. Setting it up, that's where the challenge is, okay? So let's highlight where we're at. Getting close to the end. So we had the online review. We're here today at 4.5, which is optimization. And this will be our sort of last major section on derivatives. After this, I guess we're still doing derivatives, but we're doing them backwards. So we call it an antiderivative, we call it an integral. And basically we start with the derivative, we go back to the function we've been working with. So we're just going in a different direction. And we'll start that discussion on Wednesday. Once we do that with 4.7, we only have 4 more sections for the whole course. 2 will be 5.1 and 5.2 before the next exam, which is coming up fairly quickly, just before Thanksgiving. 5.3 and 5.4 will be more applications of the integral. And we just basically have that whole last week to start doing some review. And I imagine with some people maybe heading out of town for Thanksgiving, I'll have something, we'll have the recording posted, but we'll have time in the following week to kind of get ready for the final exam. Thinking of that, as you may be starting to make travel plans to go back home or leave town after the semester's over, remember our final exam is listed as a group final exam, so it doesn't follow the standard schedule from the university. If it did, we'd be taking it on Tuesday, I think it is. Instead, we take it Thursday night of finals week, December 8th. So kind of make your travel plans around that for being here on that Thursday, December 8th. It's in the syllabus correctly, but just in case you also check the university schedule, make sure you look at the one that's called group finals, and they group us all together. I have your mastery exams ready to hand back when we're done. There were a few in there that were not what I would have preferred. They were a little trickier. They did require some algebra. I will do something, and what I'm thinking I will do is some kind of a retake for those of you, because mastery, what's mastery? What does it mean to master something? Understand it when? Sometime, right? Doesn't mean you have to understand it right now. But as long as you do by the end of the class. And that's really what I believe this is for. So I want to give some sort of incentive for those who didn't do as well as you did to kind of go back and review and get those under control. And I think it will help as we go through and we start doing things backwards. I haven't quite figured out how I'm going to do it, but I'm thinking the day that we had scheduled, that our usual final would be, is like Tuesday of finals week. Maybe have that as a day for anyone who wants to sort of do the mastery again, and I'll figure out how I'm going to do it. I don't know. It's kind of like I got to do something, so I'm telling you, but I'm not quite sure. It'll be the same type of thing where you take a 20-question derivative test. I might make it open answer rather than multiple choice, because then that gives you more freedom on just show that you know how to do it. But we'll have a discussion, okay? I could do a multiple choice one, but those are always harder to come up with. But there was at least 3 of them that were challenging because they did it in a specific way, in a way that wasn't necessary. It didn't need to be done that way. Some of it was really testing your algebra skills rather than your derivative skills. So it's supposed to test your derivative skills. So we'll make it good. Again, if you got 18 or higher, your score shows up as 100%. There's a number you at 17, and you're going to say, but that was a tricky one. If I would have got that one, I would have. So we'll talk about it, okay? So we'll have a conversation, and we'll make it fair. And today, since really there's no new skill or that we're learning, we're just going to be setting up problems. I'm going to go through, I think maybe just one, maybe two types of problems. There's, I think, 10 homework problems, and the biggest challenge is getting them set up. And so I've got one link to a resource here that will help you with a couple of them. They deal with the distance from a thing, so I'll show you that. Okay, so optimization problems, really, it just means optimize means find the maximum, find the minimum. Maximum profit, minimum cost, those kind of things if you're in business. If you're an engineer, maybe the maximum speed that is efficient, or the minimum use of fuel or something. You're trying to minimize something, maximize something. So we're going to be using concepts from 4.1 and 4.3. 4.3 talked about a lot of different derivative rules for when it's increasing, decreasing, how to tell when we've got a max or min. But the basic thing is from 4.1 and 4.3, is that whenever we have a maximum, at least a local maximum or a local minimum, the derivative will be 0, right? And then we could look both sides of the derivative to see if we're increasing and then decreasing, or vice versa, to determine whether it's maximum or minimum. You could use a second derivative test to figure out the concavity. That would also help. Or you could just graph the thing, right? The goal is if you do graph it, at least look at the calculus parts of it as well, okay? Practice with that. So that's what we're doing, and this is a quote directly from our textbook. It says, the greatest challenge, however, is to convert the word problem into mathematical optimization, into something we can go through. And so we'll look at a couple of these, but it's something that you just have to kind of challenge yourself for, go through them. Some of the problems do have that, see the solution, you could pop that down, and but see if you can kind of get a start without it. And again, I'm going to give you kind of a few hints on how to get started on some of the ones in the homework. But here's sort of the 6-step process that the text gives us. And first it's, understand the problem. So we kind of read through it. Again, sometimes with math, most of the times with math problems, I don't read it from beginning to end. I read it backwards. I find out what's the question first, and find out what the unknowns are. And then maybe you scan it for where are the numbers, right? Because those are probably going to be what we use at some point. And then maybe read over it, but kind of understand it. Also drawing diagrams. So don't be afraid to and maybe it's just a rough sketch because you don't know what it's going to look like. That's where it always kind of held me back, is I'm not sure what it's like, and so it's hard to draw that sketch, but start to draw something, and then you read it a little bit more, and then your picture becomes clearer and clearer, hopefully. We need some notation, so we get to invent some variables. Think about what the situation is. What formulas might I use? Is it involving motion of an object? Distance equals rate times time. It's going to come in here. Is it distance from one point to another point? There's a distance formula, so you kind of think of that. And various other things that come up. And they just use a general, that what we're trying to do is maximize Q. So that's the thing you're going to pick out, is every question will say to maximize or minimize something. And that's the key part. That's what we have to focus on. There might be some other unknowns, but what we're wanting to do is maximize or minimize a particular thing. And so then there's something we have control over. Okay. And this is the part it says once we've got it all set up, it's really just turn to 4.1 and 4.3. We had all those derivative tests to tell us where the minimums and maximums are. And now, in this case, since we want to optimize, we want to find the absolute maximum. absolute minimum. So there might be a local minimum or maximum, but it might not be the biggest. So we're always looking for the biggest one here. Remember, it might be at the endpoints. So that's another thing they suggest to kind of figure out what the domain is, because the domain for a particular problem will also give you access to where those endpoints are. And remember, the max or min could be happening at that endpoint. And calculus isn't going to help you with that part because you can't take the derivative at those endpoints. So we're going to use the derivative test. The main one is the first derivative test. Again, if we take the derivative, set it equal to 0, what does that give us? Critical numbers. The x values where we might have a minimum or a maximum, could have an inflection point, but those are the places we're going to look because those are the possibilities. And then also we have this added part of the first derivative test. Once we find those critical numbers, critical x values, we look to the left and we look to the right, and we can see if we're decreasing and then increasing, we're going to get a minimum, right? If we are increasing and then decreasing, we went to the top of the mountain, that's going to be a maximum. Okay, so we could do all that. And again, remember, we also can graph. And we should graph so that we get both a abstract understanding what's going on with the calculus, but we get a concrete picture. And because that's what's probably going to stay with us a lot longer, and it's what we can hang all the abstract parts to. Okay. So we're going to go with the box problem. If you had college algebra here, you will have seen this in ALEKS. If you took their ALEKS version here. I think I've also got it in my trig class. It's a pretty standard one. I do it with my math for elementary teachers. It's a great one, but I have them do it sort of like a third grader would. You get a piece of paper, you start cutting them out, and you start making boxes. So we're going to kind of do that, except we don't have to have any paper and pencil and glue stuff. We're going to do a little with an applet. So in this slide deck, there is a link to, and actually they did this, I also teach a pathways pre-calculus course, and so I'm taking some of their resources. I thought this was a really good resource because it helps you see what's going on. So what it is we've got a piece of paper, like one of these. We're going to cut squares off each of the ends, and then we fold up the sides, and we'll get a little open-ended box. Okay, and we're going to see that. And the goal is we want to maximize the volume, how much we can handle. Right? And so we're going to fold it up, and what we can vary is the amount of the cuts we make in the sides. And so we'll come here. So this is kind of the picture. We would cut out corners, we fold them up, and we get this. But let's play with this a little bit with this applet. Made with GeoGebra. It's kind of cool. So there's a slider up here where you can choose how much you're going to cut. And you can kind of see there's a maximum cut, right? Once the cut's so big it meets in the middle, you can't cut anymore, can you? What else can't you have for the size of the cut? What kind of number could you not have for a cut? Negative numbers, right? I guess you really couldn't have 0 either, because if you didn't have 0, you're not playing the game. But sort of thing. So definitely not negative. You can't do a negative cut. And then there's sort of a maximum cut depending upon the shortest side, not the longest side, because once you got in one direction. So you kind of see that with this is there's physically a limit to what you can do. But if you don't sort of draw the picture or think about it physically, you might not notice those things. Okay. And if you watch the little arrows over here, blue is the size of the cut, the red is the size of the volume that we would get. And we can see the volume goes up for a while, and then the bigger cut, we start losing volume. And so we can actually, with this, we can show, let's go ahead and show points, and we'll show the trace. So as we do this, it's kind of, we're increasing the volume, to a certain extent, and about there we start decreasing. So again, a visual of what's going on, and we come down. And notice each of the corners, what kind of a cut, what kind of a figure is that on the corners? Just square, right? So it's a square. Okay, and so there is a maximum. So what we need to do now is think in terms of this. We'll come back to our box. And let's see, how would I, so in this particular case, I started with a piece of paper that's 8.5 by 11. So how would I get the volume of the box? If I've got a box, how do I calculate its volume? Length times width times height. So that's, yeah, so that's the first thing we have to pull out of our memory is some sort of a formula, length times width times height, okay? So we're starting to introduce some variables here. We've got an idea what's going on. It's multiplication. What other thing do I need to introduce? What is varying?
The length of the square.
Okay, the length of the square. What should we call that? A. N. Okay. Good. So we'll call that N. Maybe you want to call it X, that's fine. You can call it whatever you want. N. So that's the length, the size of the cut. Okay. And if I cut in this way, I have to cut in this way as well. Now, that's not as, if you're actually physically using some scissors, you'd notice you could probably cut one more than the other, but to make a box, you really have to have them both the same. So we'll say that is a square. It's not just a rectangular corner getting cut out, it's a square. So looking at this diagram, this looks like the 8.5. I guess usually we call the length the longer side, so maybe we'll start here. So what am I doing to the 11-inch length of the paper when I cut off my corners? Making it shorter by how much? How much? 2 in, right? I'm cutting both sides. I'm cutting the left and the right side. So 2 in is getting cut off. So I can define my length to be 11 minus 2 in. Okay. So now we're starting to set up a formula that's our length. And again, you can get as formalized as you want, but I typically work less formal and just kind of scratch paper stuff. And then if I need to, I'll write it up. But if I don't, I'm okay. As long as I can kind of tell that I'm seeing that that's going to be my L, I'm okay with that. And then our width, so that would be this side here. What's going to happen there? Same thing, right? But it's 8.5, and we're going to take 2 in off of each side. And then finally, what's our height going to be? I didn't do the most important part of this box thing. This is the coolest part. You can actually fold it up. So this is the amazing part to me. I don't know how they do these things, but these animations are kind of cool. So you fold it up, and what is the height of that box? It's in. It's your cut is the height. Excellent. And you might not have seen that because, again, in the abstract world, it's just, well, I don't know. You have to see it, okay? What's really cool is once you fold it up and then you change your size of the cuts, you can actually kind of see the volume changing. And so it's kind of, again, it's nice to have these kind of applets. And when you're in your engineering, I mean, this is what they're doing with cars now too. They're making models and they're doing a lot of tests with electronic models, crash tests even, so they don't have to destroy a lot of physical stuff, and they can keep improving things, keep, off of a electronic model. Okay, so that's just going to be in here. So that's our volume, and what do we want to do with that volume? I want to find where the maximum is, and again, we kind of looked at the graph and we could see that it's not at the endpoints, because if I don't make a cut, I've got no volume. If I cut all the way to the middle, I have no volume either because there's nothing left to fold up. So the two endpoints don't help us. There's got to be somewhere in between that I get that maximum. How will I find where that is? In algebra class, we would graph this, right? And then from the graph, we'd find the maximum point. We'd see it, which is fine. A great way to do it. We want to apply our calculus. I guess that's what we're doing. I've been at a trigonometry workshop all weekend up in Cleveland, where we did do a lot of discussion about what's needed to help here, and that's what so I guess, yeah, maybe that's part of it. If I'd appreciate any input you have from thinking back to your pre-calculus class and what would have maybe been more helpful in this class, so I can get that in the next. Anyway, so how are we going to do this? Find critical points. So we have to find the derivative, right? We have to find the derivative of v. We sort of have a function now, v of n, right? This is just kind of naturally come out into being a function. Take its derivative, set it equal to 0. But what would we have to do to get the derivative of the function as it is right now? What rule? What derivative rule? Product rule. And we got 3, because there's 3 things being multiplied. We could multiply out. Again, it's up to you what you want to do. Before I take the derivative, let me see. I think I'm going to FOIL it out. Let's see. 11 times 8.5. I'm going to ask for a little bit of help. That should be 900. Oh, 8.5, not 85, yeah. 11 times 8.5. 93.5. And then 11 times negative 2n will give us negative 22n. And so we did that one. Negative 2 times 8.5 will give us negative 17n. And then 2n times 2n, negative makes it positive 4n squared. And then we've still got this n out here. So you see, once we got it set up, it's still, again, we haven't done any calculus yet, but getting it set up. So then I distribute through, it's going to give me 93.5 n. This is negative 22 and negative 17 is negative 39 n, but I'm going to multiply by this, so I'm kind of doing 2 steps at once, so I'm going to make that an n squared from the n on the outside multiplying through, not because I'm having n plus n. And then the last one becomes plus 4n to the third. Okay. So far, are we good? Okay. And again, if it was algebra, we just plug it in, we graph it from that. But yes, sir. Yeah. Sorry. I was doing 2 things at once because I don't like to rewrite. That's usually when I get myself in trouble, though, too, because I'm holding something in my mind and then I do something else and I didn't do it quite right. Or by the time I wrote it down, I messed up. Or in this case, you're going, where did that come from? Right. Okay. So yeah. So this, I was distributing this in at the same time I was cleaning up. Okay. And so now what do? Derivative, set it equal to 0. Let's get a new piece of paper here. So that's 93.5. Let's see if I can. N, what was it? It was minus 39 n squared. And then it was plus 4n cubed. Did I get everything? So we want to take its derivative. So the first part here, 93.5n, that's just going to be 93.5, right? Because this is to the first power, the one comes down. becomes into the 0, which is 1. The middle term, the 2 is going to come down. 39 times 2 is 78 in to the 1 power. And then the last one, 3 times 4, will give us 12 n squared. So that's our, what's that called? Let's call it derivative, right? Let's call it derivative. So what do we do with this? Set it equal to 0. So the derivative, we're going to set it equal to 0. And how do we find where the maximum, how do we find where the critical points are? We solve for n, right? Does that look like you could factor it very readily? I don't know. I don't think I could. Factors of 93.5. You could use a quadratic formula. How else could we solve this equation? Graphical, that's my favorite. Because we're going to graph it and we're going to find where it crosses the x-axis, right? Because it's a quadratic. So we should probably get 2 places. And I'll bet you one of them will be negative, which means we can ignore because we've already talked you can't do a negative cut. So it's not really there. But that's, yeah, so we're going to remember what we're graphing though is we're graphing the derivative, not the function itself. Let's see, let me get my Desmos up here. And this is why when we're doing the calculus, you go, well, if I'm going to need to use the graph for the algebra anyway, why don't I just graph the first thing and get the answer? But we'll play the game a little bit. Just so you understand how it goes, again, it would be perfectly okay to get that and then just to make sure that it's going to work, right? So this is y equals, what was it, 93.5 minus 78x. Again, here we use x, and then it was plus 12 x squared. And again, we're looking for, oh, there isn't a negative 1. That's okay. Okay, we've got 2 places though, but what about 4.95? Could that be a possible answer? Think about our paper is 8.5 by 5. What's the maximum cut we could do? Half of that. Half of 8.5 is like 4.25. That's too big. Okay. So I knew it was either going to be too big or negative, and I thought it would be negative, but it's not. But what does 1.585 give us? It gives us a critical value, and then what we need to do is we need to figure out is that, so we're going to take that 1.858, and again, we're going to belabor this a little bit. Let's go back to the slideshow. Where did all my writing go? It all disappeared. Okay. Come back here. So we set it equal to 0. And we found that it's going to be 0 at 1.585. And what was our original formula? What I'm kind of doing also here is, remember up here, this is our derivative. I'm going to go back and get the other function that we started with, but I'm going to start calling that the antiderivative because that's where the derivative came from. That's kind of what we'll start doing after, well, on Wednesday. So remember this was 93.5 n, and then this, since it's to the 1 power, it's going to be n to the 2nd power, which means we need to divide 78 by 2 instead of multiplying, and you'll see we'll do that. So that was 39. And then this is a 2, so we're going to add 1 to it. It's going to be n to the 3rd, And so we divide the 12 by 3, and that gave us 4, right back to where we started. Okay. And what we would do is to test out what we get, we would plug in 1.585. Back into the original function, the thing before the derivative, that's why they call it an antiderivative, and that'll give us the actual volume of the box. Again, a lot of tedious work to do that, whereas if I would have just graphed that first thing, I'd find the maximum and I'd get the answer right away, right? Which is sort of my preferred way to do it, but I also want you, and it's okay if you want to do that for the calculation parts, but just go through sort of the process to see what's the, take the derivative, find where the derivative is 0, however you go about doing that. Once you find that, plug it back into the original function, because that's the thing you've got to keep track of, is that we've got 2 functions now. We've got a derivative function, which gives us rate. We've got a original function, an antiderivative, that gives us volume. And we've got to keep them in track. Okay. Does anyone plug that in or found it? We'll graph the original one here in just a moment, but I also want to 66.15. And the units, inches, I guess, right? So what we've found is that the volume is maximized with a cut of 1.585 inches. We'll get a box that can hold 66.15 inches squared. It's not inches, it's inches squared. No, it's inches cubed. It's volume, right? So inches cubed. Okay. Part of the other question may be that they may want to know, well, okay, you've got this box, what are the dimensions of the box, right? So that could be a question. And so fortunately, mine got erased, but that's where you want to set up, well, what's the length? The length was 11 minus 2n, right? And so now we plug in n to get that length. We get 11 minus 2 times 1.585, and that'll give us our length. Our width we defined as 8.5 minus 2n, so that'll give us 8.5, minus 2 times 1.585. And I like the height is always the easiest because it's just 1.585. No calculation to do. Okay. And again, there's one in the homework that's very similar to this. The dimensions of the paper that you're using are different, but it'll be the same process. Okay. So using volume, set it up, and kind of just go through. Get a little picture. Use that little applet because that gets you more of a 3-dimensional look at it if you'd like. If you like, get a piece of paper, cut it out. Questions? Okay. So these are just going to, now instead of doing another example, because, question up here? There's a few I think in the beginning, some in the end, that talk about the distance. So they have a function, and then they have a point, and they'll either ask you to maximize that distance or minimize the distance from the graph to there. And so you're going to want to remember or use the distance formula that you're going to have 2 points. Now, one of the points may be a fixed value, and the other point may be some kind of a variable involving a function. So, and I'm going to give you a link to a place that has a few examples online, but that's our distance formula. It really comes from the Pythagorean theorem, right? If I have 2 points to get this distance, I've got a triangle, I've got the x's and I've got the y's. And And so this is x2 minus x1. If I square that, and I have y2 minus y1, and I square that, I get the hypotenuse squared, which is the distance squared. And so that's where the square root comes in, is I don't want the distance squared, I want just the distance. So that's how that formula comes about. But if you just see the formula, like me, you just go, where did that come from? It's sort of from the Pythagorean theorem. And then you add the x and y. So you'll be using that for some of the questions. And you'll see that, you know, again, this is going to be some kind of a function, so then we've got to take its derivative. We've been doing a lot of derivatives with radicals, right? Square roots. So we're going to get that 1/2 power coming down and doing those types of things. Also remember, you're going to have moving things, and you're going to want to maximize time. Especially the last problem is kind of interesting. It's someone wants to cross a circular pond, and they can swim so fast, or in a boat so fast, and they can walk so fast, and which one's going to get them there fastest, which one's going to get them there slowest, come up with a path. So you're going to be using what? Distance equals rate times time. Remember, from that formula by itself, you could also solve, you could say, well, if I know what time is, then that's going to be distance divided by rate, or I could say that the rate is the distance divided by time. So we'll use some combination of these, okay? And then this is the link, and I'm going to go ahead and go there. And I don't expect you to read all this, but that's where I copied and pasted the distance formula from there, because I didn't want to type it up. But they've got a couple problems in here, and they've got a point here on here with a point over here, and some kind of an optimization problem to which point on this graph would maybe minimize the distance from there to some other point, to 5.2. 5.2 would be here. And they've got some other curves in here, and they go through and solve the problems, or at least they're solving different things. There's one similar to this where they give you a parabola, and they want to, you make some sort of a box like this using the parabola, although you use both sides in the one we have. This is sort of half of the one, and what gives you the biggest box. So this will be a nice sort of template or a sample to help you through that one. And that's kind of what I want you to do is when you're problem solving, this is the way I do it, I look for some other resources, and I might not find exactly that same problem, which usually is not the case, but you find something close enough that gets you going. And sometimes you get something that you wouldn't have thought of, a different approach, right? That might be easier, might be harder, but so there's a couple different things. Here's a circular shape, so again, they give you kind of some formulas to think of. So I think these will be helpful in the homework problems. And remember, these homework problems, really, there are times to review what we did in 4.1 and 4.3 as far as finding max and mins. So there's, and some of these are maybe more advanced. They might be more interesting too. So let's see, let's go. Now I'll go here. And so and I remember, I guess I didn't highlight it, it's on the calendar though, this Friday is Veterans Day, so we do not meet for classes Friday. So we do have some time and some space. So it's kind of what I'm hoping you do is get started into the homework, which is just 10 problems. This last one, I actually not quite sure how to get going on this. I didn't want to, but it's kind of interesting. They've got two different rates. Let's see, she can row a boat at 3 miles per hour, but she can walk at 6 miles per hour. So what's the most convenient way? What's the best, fastest way for her to go? You can see obviously if she walks around she's got a lot further to go, but she can do that faster. She can row across, which will be shorter, but she's slower doing that. So which one is the best, or is there a combination of the two? So that's kind of an interesting one, and we've got a circle, so we'll be using the formulas and stuff for circumference probably. We'll get into there. Anyway, and there's only 2 answers needed, but it's the same type of thing. You set up your stuff, and then you're trying to minimize the time, and then actually they want you to maximize. I guess maybe she wants to, she wants to get away from some other people, so she wants to see how long she can be doing this, so all that kind of stuff. But work on those. Wednesday we will get into antiderivatives, which kind of shift the course, go backwards instead of forwards, and keep working on it. And then I've got your forms here, so I'm going to do the same thing with call out your number, but I'll go backwards. Those whose last names start with N through Z, if you come first, N through Z, just give me the number, and I got it in here somewhere.
110.
110.
I think I got 17 questions wrong.
Yes, maybe.
So, can I give the improvement one when it happens?
Well, we might do
If I
something.
get 18 right, then it would be helpful.
84.
Yes, we will. We'll figure it out. I don't know what we're going to do today because I got in at midnight and my brain is not thinking right. So but we will make it. Thank you. 107. And some of you may actually remember your numbers because I haven't been changing them, right? I think
113.
113.
So, when's the office hour again?
Right after class, I go to my office and then I'm there till at least 5:30.
All right, cool. Thank you.
98.
Thank you. 74.
4. Oh.
83.
Hi.
Hey, 87.
87. Okay.
92.
Um, 93.
94.
82. Thank you.
Was it about retaking it?
Yeah, because I had the flu last week.
Right. I got the alternate version. If you want to just come with me after class.
Yeah, sounds
Okay,
good.
perfect.
97.
97. I'm not good at multitasking.
76.
76.
109. Thank you.
I'm the other group. I'm in the
Okay.
30s.
Okay.
I came for my sweetmates paper.
Your what?
My sweetmates paper.
Okay. Okay. It's the.
Nice.
96.
I'm 53, it says.
You're in the next group. Okay.
50.
50's in the next group.
Oh.
So just in through Z, and if we run out, we'll move to the next, but it's easier to, so only over here.
Oh, I'm 43.
Okay.
103.
Six. Okay,
Yeah.
we're not there yet.
Oh. Should I wait?
Well, I guess we'll start now. It looks like the line's over. So, okay, 60. Okay, so we're looking for G through M. I'll grab that. 60. I know grades aren't showing, but still not supposed to 8, right? Okay.
Three. No, sorry, 36.
36.
43.
3. All right, right on top.
Is it my last name?
Yes.
Yeah, 71.
71. Oh, 71's here.
$55.
55.
You double check. 61. Thank you. 27. 27.
I'm supposed to tell you my name. 46, please. Thank you.
42. 39. Thank you. 49.
41. Ian with that.
If we will have some kind of a makeup or redo, I haven't decided. We will work it out. Okay.
57.
57. Space.
48.
40.
I'm 32. I didn't do very good. Is there any way I can help, like, improve my scoring?
We're
Should I
gonna-
email you or?
Let me think about it a bit. We're going to come up with a retake, some kind of a retake.
44.
33.
Hold on. 56.
19.
What's it with number 2?
Okay. Okay.
no.
Thank you.
21.
And anyone else who hasn't gotten them yet, come on down. We'll get 20. There we are.
10.
10. Sydney, right? That's why I couldn't find you, because I put the wrong number on it. But anyway, we'll get you. Okay,
14.
14.
I immediately brought it down to B. Yeah, I was like, okay, and I got to somewhere near that, I'm like, okay, if there's negative, then it's B. And then you went the other way.
5.
Double check my network.
Thank you.
I got one right. I guessed on 10. I
Oh.
think.
1 right. Five or 4.
31.
Yeah, you got stuck at that 3 over 2. And you didn't realize that 3 over 2 was 1.5.
So is this more
No. Study it, and then we'll redo it.
Are you having starts there or not?
Yeah. I'm not sure how sharp I am, but I'll be there.
I actually have a doubt. Do we get 100% if we get heading?
Yes, so it should show up there as 100%.
But for me, it shows as 60.
Send me an email, and then I'll, yeah, that should be, sometimes anyway, I can't explain it. But yes. Oh, yes, sorry.
9.
9.
Thank you.
Just looking this question for
What they did is notice you've got a.
I mean, I attempted this question many times, so I know you have to do the quotient, or you can do
Yes.
the logarithm.
But what they did is they end up factoring out, so it's going to be 1 minus x to the third. Usually you do get this, but what they did is they didn't expand the top. They let's see, there should be a 1 minus x in both of these. So this is 1. It's actually x minus. They factor it out. It ends up being. I think it's C. I'll post the answer key, but it's one of these two, and I can't remember which. I think maybe I think it's A. But that's one was tricky, is they factor it out, so it was the algebra afterwards that gets you. Yes. Well, to be honest, I got it wrong the first time too, because I was using the quotient rule. I got it out, and then it looks like one of those
I
two.
mean, is the quotient rule still the right method though?
Yes.
Okay, yeah.
That's why.
Yeah,
I
it's
mean,
just
you
the
have to.
algebra that.
And then, and the problem was with the negatives, they made it so close, and that's why I thought, oh, it's this one, and I go, oh wait, one was negative, one was positive. So they didn't have that one right. So then I saw what they did is they factored out before they multiplied out, and I thought that was tricky.
This is easy, but
This one becomes, right, e to the sine x, not just e to the x, so it's e to the sine x, and then the chain rule gives you cosine x.
I solved it right, but I'm not.
Okay.
Okay. And I just wanted to know what, how I can improve.
You're so close. I would just look at those. We're going. That's where I'm thinking is there's some that were like 16 or 17. I don't know that I would have you take the full exam again, or whether I would have you just do a few more to get to there, especially if it was those tricky ones. Hold on to it. But then there was some that missed a lot, so I am going to need to make a new test for that. But yeah, we'll do some for those that were so close to getting.
Okay.
Yeah.
Thank you.
Thank you. If you think of a good idea, throw it out at me. And
Sure.
yeah,
For like
just-
extra credit or something?
Yeah, because that's maybe what we need for those that are close. If you got a creative idea, I always like creative ideas. He gave me a few that's, he said, why don't you do this? And I was, why don't I? Good. Sure, why not? So you never know.
Yeah.
Okay, thank you. Oh, you're coming with me? Okay, good.
You wanted advice on what would be good to learn in pre-cal?
Yeah.
More algebra.
More Algebra.
just like solving through like what are they called? The thing where you have the squared.
Quadratics.
Quadratics, yes, quadratics. I feel like